Just to remind you of where we were before our test from last week, we were talking about a queue, and we were looking at how to implement a queue using an array. So we were a little bit past this point. I'm just going to go back a couple of slides to remind you. We've got a queue here. It's got 5 elements in it. So the front of the queue is, and for this particular queue, the front element of the queue happens to be the element at index 0. The back element of the queue happens to be at index 4. If you start to dequeue elements out of the queue, then elements start to come out from the front, right? So we return the element that was at the front element of the queue, and we adjust front so that it moves 1 position to the right. And if you keep on going, eventually you get to the queue where there's only 1 element in it again, right? Notice that front and back, they both point at the same element. And then if you dequeue 1 more time, front advances 1 position to the right, and you're back in the situation where front is now 1 position to the right of back. Right? Notice that in a queue that's not empty, it looks like front is always to the left of back, but that's not the case either, right? So here you might say, well, look, front is after back now, so the queue must be empty, right? This is the same situation that we had when we had an empty queue, right? Front was pointing at, front was pointing at index 0, and back was pointing at index -1. It turns out that this is not a reliable way to determine whether or not the queue is empty. You'll see why in a moment. Right. So if we start to NQ elements again, back now moves 1 to the right. Right? Insert the element, and back moves 1 to the right. And if you keep on going, the elements show up with back moving to the right. Right? And now you've reached the end of the array. Right? But the queue is not full. So there's 10 or 11 elements in this array, right? But there's still room for 5 more elements at the front of the queue, or at the front of the array. And so what do? Right? If you NQ again, back wraps around to the front again. So it turns out that back can be to the left of front in a non-empty queue, right? So just looking at the position of front and back doesn't really tell you how many elements are in the queue. You actually have to, well, it's actually easiest to keep track of the number of elements in the queue, which is what we're doing. If you keep on going, right, so back, now if you NQ more elements, back behaves the way it normally does, it moves to the right. Right? And we're now at the situation where we have a full queue. Well, sorry, we have a full array. And front is 1 position to the right of back, right, which is the same situation that we had when the queue was empty. Okay, so if you start to dequeue this queue now, right, so front is now going to move to the right. Eventually, you reach the end of the array, and the same thing happens. There's still elements in the queue, right? There's the P, Q, R, S through U. So if you dequeue again, front also wraps around to the front of the queue, to the front of the array. So it looks like we're going to have to wrap around our front and back indexes when we're NQing and dequeuing from the queue. If you draw the queue in a different way, so if you connect the front of the queue or the ends of the array together, then you end up with what's called a circular array. So in this picture of a queue, right, this is the same queue that's on the previous slide, right? So front is here, back is here. When you draw the queue in this way, front and back always move clockwise, right? Every time you NQ an operation, you add at the back of the queue. So we add an element here, back rotates 1 position to the right, or I guess clockwise, sorry. Every time you dequeue, the element comes out from the front, and then front rotates clockwise. So that's another representation of that's another visualization of a queue. We want to, back will just keep on going around and around the queue as you NQ more and more elements, right? Same with front. Okay, so how do we implement all of this? It turns out it's not very hard. Right? It's going to look a lot like a stack again. So here's our array queue class. So it's a queue implemented using a queue, right? It implements our queue interface, so it provides all the methods that are in the queue interface. And our queue is generic, so there is some unspecified type E for the element type. Internally, we have a field that is the array, It's an array of object. So remember, we can't use an array of type E because there are no generic arrays in Java. So we have to use an array of type object. We have our front and our back indexes, and we have the size of our queue. Our no argument constructor makes an empty queue. So that's pretty straightforward. We make a new array. We set front to 0. We set back to -1, and we set the size to 0. So that's straightforward. Our copy constructor copies another array queue. Right, we'll come back to this at the end of this set of lectures, at the end of this set of slides, sorry. So we have a copy constructor that can copy another array queue. So all you have to do here is you have to copy the other queue's array and its front, back, and size. So to copy the other array, you just use arrays copy of, right? You can also do this yourself manually, make a new array, write a loop, copy the elements over. Copy of, though, is easier. And then copy the value of front, back, and size from the other queue. Our methods front and back return the front element and the back element of the queue without removing them from the queue. So you can't look at the element at the front or back if the queue is empty. So if the queue is empty, we throw an exception. Right? Otherwise, you just get the element at this front or this back. Right? Now remember, our array is an array of big O object, and the user is expecting to get back an array, an element of type E. So we have to cast the value in the array to type E before we return the value. Okay, so here's DQ. So DQ is going to try to move front one position to the right every time. So if the queue is empty, that's a problem. You can't DQ an empty queue. We want to return the element that's currently at the front of the queue. So we're going to remember what that element is. Right? We're going to return it at the end of the method. So DQ returns the element that was at the front of the queue. Now we want to null out the element that's sitting at the current front of the queue. And now we want to move front one position to the right. But when we move it to the right, we have to take care of wrapping it around. So the easiest way to do this is to add 1 to this dot front. Right, so that moves it one position to the right. And if you have to wrap around, you can compute that by taking the remainder after dividing by the length of the array. Right, so for example, if you have an array of length 16, right, and this front happens to be 15, right? So that's pointing at the last valid index in the array. When you add 1 to 15, you get 16. Divide it by 16 and take the remainder, you get 0. So that effectively wraps it around back to the front of the array, right? So instead of just adding 1 to this dot front, you just add 1 to this dot front, and then take the remainder after dividing by the length of the array. The same thing's going to happen in DQ. Finally, decrease the size of the queue by 1 and return the element that was at the front of the queue. Right? The only trick here is that line there. Okay, so resizing the array. So when you enqueue an element into the queue, you may have to resize the array. If the array doesn't have enough capacity to hold the extra element, you have to resize the array, just like we had to do with a stack. This is a little bit trickier because the front and back of the queue, so the front of the queue is not necessarily at index 0. The front might be somewhere else, and that complicates things slightly. Right, so this is a picture of why this complicates things. So if this is the state of our queue, right, so it's full, so there's no room in the array for an extra element. Right, front happens to be the element in index 5, and back is the element in index 4. If you just do this way that we did with a stack, so we make a new array that's bigger than the old array, and we just copy the elements over from the old array into the new array, right? So the element 0 becomes element 0 here, element 1 becomes element 1 here, and so on and so on and so forth, right? When you look at the end of the array, you see a problem, right? So when you look at element 16 now, the value null is sitting there, which indicates that there's nothing in the array, and that you could add extra elements here, right? But this is front and back's over here. So if you start to DQ elements, when you get to the 15, right? If you dequeue again, you're going to point at the 16 now because you have extra space in the array, right? And you end up returning the wrong element. Right? You want to dequeue the q when you hit after dequeuing the p, right? But now that there's these extra elements sitting over here, the queue is not going to work properly. So your elements are now out of order at the end of the array. So what do you have to do when you copy the elements over from the old array into the new array? You have to be a little bit careful about how you do it. Okay, so one way to copy the elements correctly is to unroll the queue, right? So instead of copying the elements so that the new array looks like this, right? I want to copy the front element into index 0 of the new array, right? And then the second element into index 1, and then the third element into index 2, and so on and so on and so forth, right? So in other words, I want to unroll that array so that front is there and back is there, right? So that's a picture of what I want to do, right? So this is one way to do it. There's lots of ways you could solve this problem, right? You could copy all the elements so that the array looks like this, and then move all of these elements so that they're over here, right? Or alternatively, start copying at front. So copy 5 to here, 5 to 5, 6 to 6, 15 to 15, and then when you wrap around in the old array, copy 0 to 16, copy 1 to 17, and so on and so on and so forth. Right, so you can do it either way. It doesn't matter how you do it, as long as you make sure that the NQ and DQ operations work correctly after you copy the elements over. So I'm going to do it this way. It's not very hard to do. You just have to write your loop. You just have to pay attention to how you write your loop when you move the elements. And so the way you write your loop is up here. So if the size of the queue is equal to the capacity of the array, we need to add more capacity. So make a new array. I'm going to make it twice as big as the old array. Now copy the elements over from the array into our new array temp. So starting at index 0, going up to but not including the size of the current array, queue, right? I is going to be my index for the new array. So temp I, so temp 0 is going to be the element at the front of the queue, right? So that's going to be at this front, right? Each time you iterate, you want to add I to both that index and that index there. Right? So remember, I is the index for the new array. Right? So you just have to compute what is the corresponding element, index, in the original array. Well, that's the index at this front plus I, but don't forget we've got this wraparound issue happening. So again, take the remainder after dividing by the length of the current array, right? Not the new array, right? Notice that that's this array, it's not temp, right? It's not temp.length, it's this array.length. Alternatively, it's the size of the queue. Right. So again, just make sure you compute your index correctly, taking into account the fact that the index wraps around back to 0. Right. Once you've got that done, everything else is the same. Right. Set your array so that's equal to the new array. Right. Your front is now at index 0 and back is now at index size -1. So once you've got that done, or if you don't have to expand the size of the array, go ahead and update or insert the element at the back of the array. Right. So add 1 to back, right, taking into account that it might wrap around. So again, divide by the length of the array and take the remainder. Once you've advanced back 1 position, set the element at dispatch to the newly enqueued elements, and then add 1 to the size of the array. Sorry, to the size of the queue. Right. Okay, so in our current copy constructor, we can copy another array queue. So that's back here. Right. So if you want to copy another array queue, that's relatively straightforward. Right. You know how the array queue is implemented because you're inside the class itself. Right. So you know that there's an array that you have to copy. So you simply copy the array. What you need to keep in mind, though, is that our array queue implements this queue interface So it might be nice if you could make an array queue by copying some other queue, right? Where the other queue is not necessarily an array queue. So it could be something else. Right? It could be implemented using a linked sequence of nodes, for example, right? Or it might be implemented using a list of some kind. The problem that you run into when you try to implement this constructor is that you don't know how other is implemented. So in other words, you can't look at the fields of other. What that means is that you can only use the methods that are in the queue interface to access the elements of other. Right? And the only thing you have is NQ and DQ. Right? Furthermore, when you implement this constructor, whoever is using this constructor probably doesn't want you to change the other queue. Right? If someone's asking you to copy a queue, they probably don't want you to modify the queue that you're copying. So there's an extra constraint here. Can you implement this using only the methods of the queue interface while not permanently changing the other queue? Right. So I'll leave you to think about that for a little while. Right. Similarly, you're probably going to implement an equals method in Java. So it's easy to determine whether or not, well, sorry, is it easy? It's relatively easy to determine whether or not an array queue is equal to another array queue. Right? Again, because you know that the other array queue has an array inside of it. And you can access the fields of the other array queue. If you want to check if a queue is equal to another queue, where you don't know how the other queue is implemented, that becomes harder. Right? Again, you're in the situation where you can only use the methods of the queue interface. And again, whoever is calling equals probably doesn't want you to change the other queue. Right? So they don't want you to permanently change the other queue. And so the question is can you implement equals using only the methods of the queue interface without permanently changing the other queue? So I'll leave you to think about those two problems while we move on to the next set of slides. Anybody have any questions about implementing a queue? So all of these linear data structures, they're all very similar, right? They're just a linear sequence of elements. So a stack, a queue, and a list, they're all very similar in terms of their implementation. All right, so we'll just leave it at that. So next set of slides is 29. Okay, so just like we did with the stack, we might as well go ahead and implement a queue now using a sequence of linked nodes, right, instead of an array. So I'm going to ask you to remember back to how we implemented a stack using a linked sequence of nodes, right? So there's a picture. Oh, where's a picture? There's a picture here that we'll get to in a second. Right. Okay, so well, let's look at this picture first, and then come back to this to come back to that slide. So here's a stack implemented using a linked sequence of nodes. So in a stack, remember everything that you do with a stack, everything happens at the top of the stack, right? So when you put elements into the stack, you add them to the front of the sequence, right? So when you push an element onto the stack containing one element, right, you make a new node, right? You stick it to the front of you add it to the front of the sequence, and you make the new node. You make its next link point at the old top node. If you push another element onto the stack, you make a new node, right? Make that new node point to the old top node of the stack. So in a queue, it's exactly the same, except now when you add an element to the queue, you add it at the back, right? So you add it to the end of the sequence, right? Instead of adding to the front. But adding to the end of the sequence, that's exactly what we did with the list. So there's nothing really new here either. Right? So when you add an element to the back of the queue, right? You're going to make your new node here, and then join the current front node, or the current previous node to the new node that you just made, right? Similarly, when you enqueue again, you're going to make a new node, and then join the old back node to the new back node. Right? Notice that every time you add an element, you're adjusting the back node. Right. Similarly, when you dequeue, every time you dequeue, you're adjusting the front node. Okay, so implementing a linked queue looks a lot like implementing a stack, right? Except now you've got to keep track of an extra piece of information, right? So in a stack, we kept track of the top of the stack, right? In a queue, we need to keep track of the front and the back, right? Because in a queue, operations happen at both the front and the back of the queue. So we need to know what is the current front node, what is the current back node. Right? Again, we have a private, sorry, there's a bug here. We have a private static nested class that represents the node, just like we did with the stack. Right? So inside of our node, we've got an element, we have the next link, and we've got our constructor. The only difference here is that this is now generic. So we did a generic stack as well, right? Yeah, so there's not really any difference here, right? So your node is generic, right? It holds some element of type E, right? Which is the same type of element that your queue is holding. All right, so the no argument constructor makes a new empty queue. So it sets the size to 0. There's no front or back node. So it simply sets those values to null. Front and back, return the front and back element of the queue without removing them from the queue. Now we have a reference to the front element, so I can to the front node, so I can just return front.elem. Right. Similarly, we have a reference to the back node, so I can just return back.elem. Okay, so what does in queue look like? Okay, so in queue, looks a lot like the stack version of push. Right. Make a new node. Oops, sorry. Make a new node, right, and hook it up to the current front of the queue. Right. So ignore the special case for now. Ignore these the two parts of the if statement for now. So we're going to make our new node. So our new node holds the element that we're enqueuing, right? And the next link of that node points nowhere for now, right? Enqueue, sorry, enqueue. Oh wait, sorry, I screwed that up. Enqueue adds to the back. Here we go. Right, so enqueue adds to the back. So you're going to make a new node. You're going to hook up the current front node so that it points at your new node here. Right. So there's our new node. Right. Its next link points nowhere because it's going to be the new back of the node. Right. So down here, we're going to update back so that it's now equal to n, right? Because that's our new back node. We're going to increase the size of the queue by 1 because we just added an element to the queue. Right. Now, if the queue has stuff in it, then all you have to do is update this.back.next. So back here. Right. So when the queue has one element in it, right, the back node is the node A. Right. When you enqueue a new element into it, you make your new node, and then you adjust this.back.next so that it points at the new node here. Right. When you enqueue again, that's our current back node. Right. So we write this.back.next is equal to the new node that we just added. Right. So if the queue has stuff in it, you can just write this.back.next equals n. If the queue is empty, you have a special case. Right. So if the queue is empty, you have to write, you have to adjust the front node as well. So going back to here. So if you have an empty queue, which would be up here, right, front and back are both null. So when you add one element to that queue, you end up with the picture, the top row of the picture, right, where front points at the new node and back also points at the new node, right? If there's stuff in the queue, you never adjust front, right? So when stuff's in the queue, you're only adjusting back. So there is a special case when you have an empty queue, right? You also have to adjust this dot front so that it refers to or points at the new node. Right. Now, if you look at the picture, you might think that there's also a special case when the size is equal to 1. Right. And so it's a little deceptive. So when the size is equal to 1, right, and you add a new element to the back of the queue, right, so you end up in the second row here, it looks like you're adjusting the next link of front as well, right? So it looks like when you have a queue of size 1, you have to write this dot front dot next equals back, right? But that's not true, right? That's why this question mark is here, right? Do you actually have to do this? The answer is no, right? And why is the answer no, right? And what you have to remember is that this dot front and this dot back, they are both references to a node, right? So remember that they're not actually the node itself, right? It's a reference to a node. So when there's one element in the queue, right, there's only one node, right? There's not two nodes, right? Front happens to point at A, back also happens to point at A, right? So if you adjust this dot back dot next, right, you're adjusting the next link of that node, okay, which is the same node that front points at, right? So if writing this dot back dot next or writing this dot front dot next adjusts the next link of that node. It doesn't matter which one you use to adjust the link, right? It does the same thing. It changes that link so that it points at the new back node. So that special case here is in fact not a special case, right? You can strike the else if part from that method there, right? You only ever have to adjust the next link of the back node. All right, what about DQ? So DQ is exactly like popping an element off a stack. So there's nothing new here. Right, so to pop the element off the top of a stack, you remember what is the current element at the top. So to DQ an element from the front of a queue, you remember what is the element at the front of the queue. Right? Later on, you're going to return the element at the end. Okay. So when you remove from the front of a queue, you have to adjust this dot front. Do I have a DQ picture? I don't have a DQ picture here, sorry. So to adjust this dot front, you just make front point at the next element in the sequence. Right. So this dot front is equal to front dot next. Okay. So that's the second node in the sequence. So this dot front now points at the second node of the sequence. Remove one from the size of the queue, right? And again, you have a special case. Right, so when you DQ a queue, normally you adjust only the front node, right? But if your queue becomes empty, then you have to remember you're also keeping track of where the back node is. So now you have to indicate that the back node is now no longer existing, right? So if your queue is now empty, this dot back has to become null, right? If you forget to adjust this dot back, right, this dot back is pointing at the old last node or the old front node in this case. Right, and then when you go to NQ again, you're going to end up with an incorrect queue. Right. So there's in these data structures, you're always trying to look for these special cases. Typically, they happen when the data structure becomes empty. There's something that you have to adjust as a special case. Okay, so why did we go through the trouble of implementing a queue using a linked sequence of nodes? Number one, because it's good for you to learn how to do this. But number two, you end up with an NQ and a DQ operation that are both in constant time, right? So now NQ and DQ are both constant time. When you look at the methods, there's nothing here that takes time proportional to the length of the queue, right? All that you're doing is so to DQ, there's just a few assignment statements and an if statement, right? For NQ, there's making a new node, but then there's some if statements and some assignments. Right, nothing here that's proportional to the size of the queue. So for NQ, you have guaranteed O1 complexity, which is better than in an array-based queue. Right, remember in an array-based queue, every once in a while you have to expand the size of the array, which takes time proportional to the number of elements in the queue. DQ has the same computational complexity as for an array-based queue. So the advantage of using a linked sequence of nodes is that you have guaranteed constant complexity for NQ. Okay, any questions about queues? All right, moving right along. Generic methods. So I'm just wondering if this is a good time to go back. No, let's do this first. I want to go back eventually and do sets and maps because it's kind of important that you know how to use those things in Java. But we skipped over those earlier in the course. So at some point, we have to go back and talk about them. I think I'll talk about them after I tell you about generic methods. So we've implemented a generic interface. We've implemented a generic class. Right? In Java, you can also have methods that are generic. So a generic method is simply a method that has its own type variables. You can have a generic method inside of a generic class, but for simplicity, I'm going to make some generic methods in a regular class. Right? So just like a generic class has its own type variables, every method can also have its own type variables. So if you create a generic method, the type variables for each method are independent of all other methods, right? So in other words, the generic type variables apply only to the method that you're writing. And these sort of things show up often in utility classes, especially in the standard library. So in the standard library, you've got this class called collections with an S. Right? That's the utility class that operates on Java collections, so lists and sets. If you look inside that class, all of the methods are marked as generic methods. The same is true in arrays. The same is true in objects. Right? Many of the methods in arrays operate on arrays where the element type is some unspecified type, right? So it's a generic method. Okay, so what does a generic method look like? It looks like exactly like a regular method, except it has its type variables somewhere in the header, right? So just like in a generic class, you have to put the angle brackets in and then the name of a type variable. A generic method also has this notation, right? And so in a generic method, the type variables appear before the return type. So following the standard library, we're going to cook up a utility class that operates on stacks, right? So just like the standard library has a utility class that operates on collections, we've implemented some stacks. So let's make some methods that operate on stacks. Right? So the first thing that we're going to do is we're going to write a method that clears a stack, right? Because our stack class or our stack interface doesn't have a method that empties the stack. And so here, we'll add that method in a utility class instead. All right, so here's how you create a generic method. So here I have a regular class called stacks. The class is going to be a utility class, so everything inside this class will be static. Here's my clear method. Right, so clear takes in a stack of some element type t. Right. Notice that the class itself is not generic. Right. You've got a generic type here, so this method needs to be generic, and so you insert the generic type variable here. Right. So when you only need to do this when you're making a generic method, right? So when you're making regular methods inside of a generic class, right, you don't mark the methods as being generic, right? The class is already generic, right? But when you're making a method that you want to be generic, independent of the type that's in the class, right, you have to mark the method as being generic now. So notice there's not really anything you have to do here to make this method generic, right? You just stick in the type variable here and everything stays the same. Okay, so how do you implement clear? So clear is supposed to empty the stack. You don't know what kind of stack it is, right? So you don't know if it's a linked stack or an array-based stack or a list-based stack. It's just a stack of some kind. So to implement the method, you can only use the methods that are in the stack interface itself. Right? Fortunately, this is easy, right? As long as the stack is not empty, pop the stack, right? And that removes all the elements from the stack. Notice that inside the method, that type t never appears. Right? So we don't actually care about the type of stack in this particular method, right? The element type in the stack in this particular method, right? But we still have the generic notation here. Okay, so let's look at another example of a generic method. So this one, we're actually going to use the type information. So we want to create a method called push all. So here, the user or the caller has some kind of collection. So they have a set or a list of stuff. and they would like to take all the elements in the collection and add them to our stack. Right. The method should not remove the elements from the collection, right? It simply wants to take the elements in the collection and put them on the stack. Here, the element type of the collection and the element type of the stack matters, right? You need the element types to match, question mark. Right. So in other words, if you have a list of string, you shouldn't be able to add those elements to a stack of integer, right? The types have to match. So here, right, the element type of your collection must match, again, question mark, the element type of your stack. Right. So that T and that T are the same. Now this method is generic, so I have to indicate that it's generic by adding the type variable to the front. Right. Now inside the method, T actually appears as a type, right? Because what I want to do is I want to iterate over the source collection. Each time I iterate over the elements of the collection, I want to add them or push them onto the stack. Right. So for each element in the source collection, right, push the element onto the stack. Right. Again, notice, right, the power of Java generics and inheritance here, right? You can write this little loop here. You can write this little for each loop here, right? This loop is guaranteed to work, right? Why? Because we know that every collection implements the iterable interface, right? So that means you can write a for each loop over any collection. Okay, one more time, one more example, pop all. So here you've got a stack and a collection. You'd like to remove all the elements from the stack and now add them to the collection. So you want to do the opposite. Right, this time we're actually going to remove the elements from the stack. Right, but you're not going to remove any elements from the collection. Right, again, type safety matters here. If you have a stack of string, you shouldn't be able to pop the stack and add it to a list of integer, for example. So again, it looks like our element types must match the element types. The element types for the stack must match the element type of the collection. Right. So here, our source collection is our stack, or our source. Our source object is our stack. Right. Our destination object is a collection of some kind. Again, because our source and destination objects are generic, the method again has to be marked generic. Okay. How do you implement the method? As long it's the same as clear, except instead, and when you pop the element off of source, you're just going to add it to the destination collection. Okay. So pop the source stack, adding the element to the destination collection. Right. Again, notice the power of inheritance here, or I guess interfaces, right? Why can we write add? Because every collection has an add method. So it doesn't matter if it's a list or a set, right? That line of code just works. All right, any questions so far? So far, everything, our methods are just plain old methods, right? The only difference is that you're adding the generic type here. Okay, so something slightly more complicated. So if you decide that you want to be able to test if a stack contains an element, you run into some problems, right? So the problem that you run into is that if you want to test if a stack contains an element, what you really want to do is you want to iterate over the elements of the stack. But our stack type doesn't provide the iterable interface. So there's no iterator over stacks for our types. Now you could go back and change our stacks so that they did implement an iterator, right? But if they don't, you're now stuck in this situation where you have to implement contains. So in other words, you have to iterate over the sequence of a stack without having an iterator and without knowing how the stack is implemented. Right? So you don't know if it's an array-based stack. You don't know if it's a list-based stack. You don't know if it's a node-based stack, right? And even if you did, that doesn't help you because you don't have access to the private members of those classes anyway. Right? So this becomes very inconvenient to implement. You don't have access to the private fields of the stacks, right? There's no iterator over the stacks, right? When you implement contains, whoever's calling the method probably doesn't want you to change the stack permanently. And so you're in a similar situation to the end of the last slide, right, where I left you with the questions: how do you implement a copy constructor for a array queue? How do you implement equals for an array queue? Right. So here you have to get a little clever, right? So the idea here is, if I'm going to search a stack for an element, the only way I can look at the elements is to pop them off the stack. So I'm going to pop the elements of the input stack onto a brand new temporary stack, right? And I'm going to do this until I find the thing that I'm looking for, or until the input stack is empty, right? I'm then going to undo the process. So I'm then going to pop all the elements off the temporary stack and put them back onto the original stack, right? And that leaves the original stack unchanged, and it does, in fact, correctly search for the element that we're looking for. Right. So here's a picture here. The blue stack is always the original stack, so it's always the input stack. The stack in black is always the temporary stack. So if I want to test, does this stack contain the string Z? Right. Make a temporary stack and start popping elements off of the input stack. Right. So you pop the D. You test, is the D equal to the Z? The answer is no, so you put the D into the temporary stack. Right. Now, your original stack is not empty. You still haven't found the Z, so you pop the original stack. That's the C. Is the C equal to the Z? The answer is no, so you plunk it into the temporary stack. Right. Pop the B. Is it equal to the Z? The answer is no. Push it onto the temporary stack. Pop the A. Is it equal to Z? The answer is no. Push it onto the temporary stack. And now your original stack is empty. Right. You also know the answer is false. Right. The original stack did not contain Z. Now your job is to restore S back to its original state. So simply pop the elements off of temp and push them back onto S. Right. Oh, wait, I had a picture here. I didn't realize this was animated. Okay, never mind. Okay, so back in reverse. Right. So now S is empty. I just want to pop the elements off of temp into S. Right. So pop the A out off the temp, push it onto S. Pop the B, pop the C, and pop the D, right? And now you've got your original stack back in its original order. Okay, so to implement contains, right, it's kind of awkward. You make a new stack. Doesn't matter what kind of stack you make, they all work. I'm just going to use array stack. Right. While the original stack is not empty, so while its size was greater than 0, right, and you have not found the element you're looking for, right, pop the original stack. Right. Test if the element that was popped is equal to the thing that you're looking for. Right. If it is, return your result is true. Right, and that will stop the loop on its from running anymore. Right. Regardless of whether or not the thing that you're looking for, regardless of whether or not you found the thing that you're looking for, I'm going to push the element on the temporary stack. Right. When this loop is done, either you found the thing that you're looking for and there's still stuff left on the original stack, or the original stack is empty. It doesn't matter what situation you're in. As long as there's stuff in the temporary stack, you're just going to pop the temporary stack and push it back onto the original stack. Right. And so implementing this method becomes slightly awkward. Right. Again, because you don't know what kind of stack S is, right? And you don't, and even if you did know, you don't have access to its fields anyway. Okay. We can do the exact same thing for queues. Right. So you can create a little utility class called queues and implement similar methods, right? So clear will clear a queue, and queue all adds all the elements from source into the destination queue. Dequeue all takes all the elements out of source and adds them to the destination collection. Contains does the exact same thing that contains does for a stack, right? It searches a queue for some object obj. Right. So again, we have a regular class. It's not generic. Our clear method is generic, so we add its generic type here. Right. Implementing this is easy, right? As long as the queue has something in it, simply dequeue the queue. Notice that we're not using the element type T anywhere inside the method. For NQ all, we've got a source collection where we want to take its elements and add it to the destination queue, right? The element types here have to match, right? Again, you can't have a collection of strings and add that to a queue of integers. Again, the implementation is exactly the same, or almost exactly the same as for a stack. Just iterate over the source collection, right? And queuing elements as you go. DQ all, again, is like pop all. Sorry, DQ, yes, is like pop all, right? You have a source queue, you've got a destination collection, right? Again, your types have to match. Implementing the method is just a little loop, right? So while there's stuff in the source queue, DQ the queue, add the element to the destination collection. Right. Finally, contains. So contains, you're in a similar situation as you are with a stack, right? There is no iterator for our queue class, so I can't write a simple loop to do this, right? I don't know how the queues are implemented, so I can't access their private fields. I don't want to permanently modify the input queue either if I'm searching for an element, right? So whatever I do to the queue, I have to undo the change. Now, unlike a stack, you don't need a temporary data structure here, right? So here we can exploit the fact that when you take an element out of a queue, so here we exploit the fact that you know how many elements are in the queue. When you take an element out, you just stick it right back in again, right? So if you loop for a number of times equal to the size of the queue, right, that will take all the elements out of the queue and put them back into the queue, and you're left with the queue back in its original order. Right. So for every element that's in the queue, DQ the queue, right? If it's equal to the thing you're looking for, you know that your answer is true, but you keep on going, right? You have to keep on going so that you can put all the elements back in the queue, right? It's useful to store the result here and test if the result is false, right? So this is saying if the result is false, right, then check if the element is equal. Right, if result is true, then the way that AND works here is that the equals is never called. Right. Sorry, if not result, right, if result is false, then you know that this entire expression is also false. So elem equals object never happens. Okay, once you've tested the element, simply enqueue the element back into the queue. Right, when this loop is done, you know your answer. You can just return the result, and the original queue is left unchanged.